Hello, myself Bharathraj. I am going to talk about the topic ferments and Euler's theorem. In this PPT, we are going to see about prime numbers, ferments theorem, Euler's tuition function, Euler's theorem. First, we are going to see about prime numbers. Prime numbers only have divisors of 1 and self. They can't be written as a product of other numbers. Next, prime factorization. To factor a number n is to write it as a product of other numbers n equal to a into b into c. Like example, 100 can be written as 5 into 5 into 2 into 2. Prime factorization of number n is written it as a product of prime numbers. Example 143 can be written as 11 into 13. And this is the formula used for prime factorization. Relatively prime number. Two numbers are relatively prime if they have no common divisors other than 1. 10 and 21 are relatively prime in respect to each other as 10 has factor of 1, 2, 5, 10 and 21 has factor of 1, 3, 7, 21. The greatest common divisor of two relatively prime numbers can be determined by comparing their prime factorization and selecting the least powers. Next, we are going to see about Fermat's theorem. Like Fermat's little theorem is a fundamental theorem in elementary number theorem, which provides compute powers of integer modulo prime numbers. It is a specific case of Euler's theorem and is essential in application of elementary number theorem such as preliminary testing and public key cryptography. This is referred as a Fermat's little theorem. Fermat's little theorem states that p is a prime number, then for any integer a, the number a p minus a is an integer multiple of p. Here p is a prime number. Now ap is equivalent to a of mod p. In some special cases, if a is not divisible by p, Fermat's little theorem is equivalent to the statement that a p minus 1 is an integer multiple of p. ap minus 1 is equivalent to 1 of mod p, or ap minus 1 percentage p equal to 1. Here a is not divisible by p. Fermat's little theorem shows that if is prime, there does not exist a base with such that possesses a non-zero residue modulo. If such base exists, is therefore granted to be composite. However, the lack of non-zero residue in Fermat's little theorem does not guarantee that is prime. The property of unambiguously certifying composite numbers while passing some prime make Fermat's little theorem a compositeness test, which is sometimes called the Fermat compositeness test. A number satisfying Fermat's little theorem for some non-trivial base and which is not known be a composite is called a probable prime. Composite numbers known as Fermat pseudo primes have zero residue for some s and so are not identified as composite. Worse still, there are exist number known as Carmichael numbers, the smallest of which is 561, which give zero residue for any choice of the base relatively prime 2. However, Fermat's little theorem converse provides a criterion for certifying the primarily of a number. For example, p equal to an integer prime number, a equal to an integer which is not multiple of p. Let a equal to 2 and p equal to 17. According to Fermat's little theorem, 2 17 minus 1 is equivalent to 1 mod of 17. By equating this, we got 65 36 percentage of 17 equivalent to 1. That means 65536 minus 1 is an multiple of 17. Let's see about the proof of Fermat's little theorem. Proof by counting. We are going to see the proof by counting necklace. This is known proof Requiring the least mathematical background, it is an attractive example of compositional proof, a proof that involves counting a collection of objects in two different ways. The proof given here is an adaptation of Goulam's proof. To keep these things simple, let us assume that A is a positive integer. Consider all the possible strings of P symbols using an alphabet with A different symbols. The total number of such strings is A power B, since there are A possibilities for each of P positions. For example, if P equal to 5 and A equal to 2, then we can use an alphabet with two symbols. And there are 2 power 5 equal to 32 strings of length 5. These are the strings of length 5. We will argue below that if we remove the string consisting of single symbol from the list, for example, if you are going to remove A of 5 and B of 5, if the remaining A power P minus A strings can be arranged into groups, each group containing exactly P strings. It follows that A power P minus A is divisible by P. Let us think of each such string as representing a necklace. That is, we connect the two ends of the string together and regard two strings as the same necklace. If we can rotate one string to obtain the second string, in the case we will see that the two strings are friends. In our example, the following strings are all friends. In full, each line of the following list corresponds to a single necklace, and the entire list comprises of all 32 strings, that including the 5 of A and 5 of B. Notice that in the above list, each necklace with more than one symbol is represented by 5 different strings, and the number of necklaces represented by just one string is the number of distinct symbols. Thus, the list shows very clearly why 32 minus 2 is divisible by 5. One can use the following rule to work out how many friends a given string S has. If S is built up of several copies of the string T cannot itself be broken down further into repeating strings, then the number of friends of S is equal to the length of T. For example, suppose we start with the string S equal to the A B like that, which is built up of several copies of the shorter string T equal to ABB. If we rotate it one symbol at a time, we obtain the following three strings. They are not any others because ABB is exactly three symbols long and cannot be broken down into further repeating strings. Using the above rule, we can complete the proof of Fermat's little theorem quite easily as follows. Our starting pool of A power P strings may be split into two categories. Some strings contain P identical symbols. There are exactly A of this, one for each symbol in the alphabet. The rest of the strings use at least two distinct symbols from the alphabet. If we can break up S into repeating copies of some string T, the length of T must divide the length of S. But since the length of S is the prime P, the only possible length for T is also P. Therefore, the above rule tells us the S has exactly P friends, including S itself. The second category contains A power P minus A strings, and they may be arranged into groups of P strings, one group for each necklace. Therefore, A power P minus A must be divisible by P as promised. Next, we are going to see about Euler's torsion function. Euler's torsion function is the mathematical multiplicative function which counts the positive integer up to the given integer, generally known as n, that are a prime number to n, and the function can be used to represent the number of prime numbers that exist up the given integer n. Euler's torsion function is also called as Euler's pi function. It plays an essential role in cryptography. It can discover the number of integers that are both smaller than n and relatively prime to n. Euler's torsion function is beneficially in several ways. It can be used in the RSA encryption system, which can be used for security goals. The function deals with the prime number theory, and it is beneficially in the computation of large calculations also. The functions can be utilized in algebraic computation and simple numbers. The symbol used to indicate the function is pi. The function includes more theoretical use instead of practical use. The sensible requirement of the function is limited. The function can be better understood through the several practical examples instead of only theoretical explanation. There are several rules for computing the Euler's torsion function, and for different numbers, different rules are to be used. And the torsion function calculates the number of elements in Zn with the help of following rules. Pi of 1 equal to 0, like pi of p equal to p minus 1. These are the rules followed by Euler's torsion function to calculate the number of elements. Next, we are going to see about Euler's theorem. Euler's theorem is a generalization of Fermat's little theorem handling with the power of integer modulo positive integers. It increases in application of elementary number theory, such as the theoretical supporting structure for the RSA crypto system. This theorem states that for every a and n that are relatively prime, a power pi of n equivalent to 1 of mod n, where pi of n is Euler's torsion function, which counts the number of positive integers less than n that are relatively prime to n. For example, we can take 6 is an perfect number, so it can be written in the form of 22 minus 1 star of 2 minus 1 equal to 6, where n equal to 2 is a prime number and 2 power n minus 1 equal to 3 is a Mersenne prime number. Likewise, we can calculate for 28 also. Next, proof for Euler's theorem. Euler's theorem can be proven using concept from the theory of groups. The residue classes modulo n that are co-prime to n form a group under multiplication. The order of that group is P of n. Lagrange's theorem states that the order of any subgroup of a finite group divides the order of the entire group. In the case of P of n, if A is any number co-prime to n, then A is in one of these residue classes and its powers a square up to a power k. Modulo n form a subgroup of the group of residue classes with a power k equivalent to 1 of mod of n. Lagrange's theorem says k must divide p of n. There is an integer m such that k of m equal to p of n. This then implies this implies the proof of a power p of n equal to a power km equal to a of k of m equivalent to 1 power m equal to 1 equivalent to 1 of mod n. Another proof, let's see about the another proof. If there is an also a direct proof, let r equal to x1 x2 up to we can take up xp of n be a reduced residue system of mode of n, and let a be any integer co-prime to n. The proof hinges on the fundamental fact that multiplication by a primitives the x. In other words, if ax j equivalent to ax k mod of n, then j equal to k. That is the sets R and A are equal to ax1 comma ax2 up to ax p of n. Consider a set of conjurance classes are identical, so the product of all the numbers in R is to the products of all the numbers in AR, and this is the proof we are getting from this. Next, we are going to see about the application. There are three applications of Fermat's little theorem and Euler's generalization, like primitive testing, party tricks, RSA public key encryption. Like primary testing, the contrapositive of Fermat's little theorem is useful in preliminary testing. If a conjunction A p minus 1 equal to 1 of mod p does not hold, then either p is not prime or a is a multiple of p. In practice, a is much smaller than p, and so one can conclude that p is not prime. Technically, this is a test for non-primitive. It can only prove that a number is not prime. For example, if 2p minus 1 is not conjunct to 1 of mod p, then we know p is not a prime. But if 2p minus 1 is conjunct to 1 of mod p, then all we know is that we have not failed the test. It is still conceivable that p is prime. So we try another value of a, so say 3, and see whether 3p minus 1 is conjugate to b of 1 of mod of p. If we have not disproved that p is a prime after several attempts, we have reason to believe p is probably prime. There are pseudo primes and commercial numbers that are not prime but pass the primitive test above for all the values of a, but this number of much less than common that primes. By the way, if p is a huge number, say with hundreds or thousands of digits, does not it seems odd, then we would want to compute number to be power p. Actually, computing AP would be impossible, but because we are computing mod P, this is actually easy. We can apply the fast exponentiation algorithm and take remainder by P at every steps. So we are never working with numbers more than twice as possible as long as P. Next, we are going to see about pottery tricks. A few days ago, I wrote about the fifth road pottery tricks. If someone raises a two-digit number to the fifth power, you can quickly tell what the number was. Part of what makes the trick work is that in base 10, any number n and its fifth power end in the same digit. You can prove this by trying all possible last digit, but if you want to generalize the trick to other bases, it helps to use Euler's theorem. For example, you could use ninth power in the base 15. Euler's theorem shows why raising a to the power pi of m plus 1 in the base m keeps the last digit the same, but only if a is relatively prime to m. To extend the fifth row trick to other bases, you will have a little more work to do. Next, we are going to see about RSA encryption. The original RSA public key cryptography algorithm was a clever use of Euler's theorem. Search for two enormous prime number P and Q. Keep P and Q private but make n equal to PQ public. Like if pick a private key D and solve for a public key E such that D equal to 1 of mod pi of n. Since you know P and Q, you can compute pi of n equal to p minus 1 q minus 1, and so you can compute the public key E. But someone who does not know p and q but only their product n, we have a hard time solving for D from knowing E, or at least that's the hope. Being able to factor n is sufficient to break the encryption scheme, but it is not logically necessary. Maybe recovering private key is much easier than factoring that does not seem to be the case. This is the basic idea of RSA encryption, but there are many practical details to implement the RSA algorithm well. For example, you don't want P and Q to be prime, that makes PQ easier than usual to factor. So you want to use safe primes. Like summary, we firstly prime numbers, prime factorization and greatest common divisor were discussed. Secondly, Fermat's theorem and its proof is done. Then Euler's torsion function is discussed, and lastly Euler's theorem is discussed. Thank you, sir. Thank you for spending time to watch the video.